This week we're going to talk about earthquakes. And so last week we talked a little bit about structural geology. So we did mention faulting and things like that. So now we're going to spend a little more time just focusing on those features, the faults, the brittle deformation, because those impact us more than, let's say, a fold, because those are occurring usually at depth because we need that high temperature. So let's see, we're going to cruise through some stuff. So there's a lot of stuff here. Well, it'll depend if I make one or two videos how long this gets, but we want to cover the earthquakes themselves. We want to cover some of the hazards associated with earthquakes, and then we want to talk a little bit about prediction. And so why do we care about seismology or earthquakes, right? Well, because we know they impact people and society. We'd like to know when and where they occur. We'd also like to know where we should build our buildings. If there's different places that react differently, we would like to know that so we can check out how the rocks behave or different materials behave when an earthquake occurs. It, of course, tells us something about the interior of the earth. So way back when we first started, we did do a little module on the interior of the earth. And we said that when earthquakes occur, they give out energy waves. Those move through the earth and they can give us some information about what's inside. Because, of course, we can't drill down deep enough to sample, we use this kind of remote sensing technique. So this is why earthquakes can be useful. So the idea behind earthquakes and what we see occurring is this theory called elastic rebound. And really what it's suggesting is that as the rocks get compressed, or in some cases pulled apart, or even sheared, right? So those are our three types of stresses that we can apply, that the rocks actually will deform. And so they'll actually bend or bow a little bit, even though we're brittle here and we know we're near the surface, cooler temperatures and things like that. But the rocks will still deform. The idea is, though, they're deforming kind of slightly, not these huge deformation events, but it's happening over long periods of time, right? So years, 10, 20, hundreds of years of stress is slowly deforming the rock. It might bulge up a little, it might shift to the left a little, but what will finally happen is there's so much stress that the rock can't deform anymore. It's reached its limit, and then it'll break, it'll slip, it'll crack, it'll fracture, and the rock will actually bounce back to its original position. And so this is this idea of rebounding. And the rebounding event is what gives off the energy that propagates out in all directions. And so I don't have a little clip, but if you can imagine with me for a minute, if I had a wooden meter stick, you can see that if I grab the ends of it, I can bend that. I can bow it. I can change its shape from a nice little linear feature to a kind of an arc even. So it starts to bend. Now that's a brittle thing. If I said, here's a piece of wood, is it brittle? You would say yes. But it deforms first before it reacts brittly. And so this is what the rocks are doing. We look at rocks and say, yes, that's brittle, but they also have the potential to bend. And so when I bend my meter stick into kind of this arc shape, that bending is storing the energy. And so if I exceed what it can bend and then I snap my meter stick in half, if I look at each half, they're not bent anymore. They're now linear. They're straight. I have two straight pieces. And so what happened was the material rebounded back to its original position, and in doing so, it gave off energy. So there is a correlation here between the amount of deformation and the size of the earthquake. So the longer I can apply stress and the more stress the rocks can store, the bigger the earthquake we can get. And so we can use that sometimes to determine, size of earthquakes or potential size of earthquakes in certain areas. So this is a little bit of a review. We know something about where earthquakes occur because we know about plate tectonics. We also can identify different types of faults. And so we said that there is a normal, a reverse. I know it says thrust fault there, but we're interchanging those. We have a compressional event gives us this, a tensional event, and a shearing event gives us the strike slip. We see earthquakes occurring in general where the stresses are the highest, where plates are interacting. That kind of makes sense. And so when we have an earthquake that occurs, we actually have two kind of points that we want to identify. You've heard of the epicenter, I'm sure, and that's a point on the surface that identifies a location of the earthquake, but it's not the true place where the rupture actually occurred, and that's actually the focus. So using seismograms and other instruments, we can determine where the rock first broke at depth. And once we identify that, we just draw a line straight up, and when it hits the surface, we say, oh, that's the epicenter. And we just use that because it's a geographic location. You know, it's Napa Valley or it's Phoenix, Arizona, so we can tell people where the earthquake occurred. So when earthquakes happen, there are lots of energy waves that are created from this event. So we're not going to talk about all of them, but we're going to talk about the few that are important to us. And you've kind of heard these before because the body waves were the energy waves that propagate throughout the entire body of the Earth. And so those gave us some information about the interior of the Earth. Well, of course, they also help us with some things here when we see them recorded on a seismograph. And so the two body waves that we just want to talk about, and like I said, we've mentioned these before, but there's what's called the P wave, which is a compressional wave. It's transmitting its energy through a compressional force, which tends to be pretty efficient. And so it moves pretty quickly. You can see the speed there is pretty fast. Moves through solids and liquids. At this point, we don't really care too much about that. It's really about the speed. This is the fastest wave, energy wave that is generated during an earthquake. And then we get a secondary wave or a shear wave or an S wave. We like any of those names for it. It also propagates out from the focus. It's a little slower because of the way it transmits its energy. It's more shearing motion. It's not as efficient, so it's slower. But these waves can be recorded on a seismogram, right? So we can use that information to help us locate, number one, where the earthquake occurred, and also give us some idea of the magnitude of the earthquake. How big was it? Now, there are some other waves that impact society and kind of the Earth's surface. And so the two we just mentioned were body waves moving through the body of the Earth. We have surface waves that actually stick near the surface and propagate around the surface. Now, the thing about surface waves, there's two main types of those. They're called the Love and the Rayleigh wave. They move a little differently too. These tend to be slow waves compared to the others, and which means that they tend to do more damage than the others. So the P wave, not so much. Because it's so fast, it moves through really quickly. S wave, some damage there, but the P wave for sure has a lot of damage because it's a slow moving wave and it's moving the Earth up and down and side to side, and that can cause a lot of damage. And so what do we do when we have an earthquake? Well, we use instruments to record the ground motion, and we can get vertical and horizontal because we have different waves that are moving through. And so we want to use this to locate the epicenter of an earthquake. So they look something like this, where you would have a line on a computer that's just pretty flat, but when there's a deflection and it moves up and down, it's indicating that the ground is moving in a certain direction. And we can record the two different waves that show up here. So I'm going to give you a kind of a more idealized, I guess, seismogram. So this would be something you might see where there's nothing happening, and then you can see there's some event that's occurred here, and then another event, and then even a bigger event. So what are those things? We can identify them in general as P waves, S waves, and surface waves. So how does this help me determine where the epicenter of an earthquake is? It's really the arrival time, and we're going to call the time that the P wave arrives and the time of the S wave arrives. The difference between those arrival time, called the lag time, is going to actually tell us something about how close my instrument is to the earthquake. So think about this for a minute. If there's an earthquake and we're really close, what's going to happen is the P and the S wave will arrive at my station fairly close together. P, S, boom, boom. Let's say I'm, 20 kilometers away or something. But if I'm 300 kilometers away, hopefully you can see that the P wave would arrive, and then maybe 30 seconds later, the S wave would arrive. So the longer the lag time, the difference between those arrivals of the S and the P, tells us I'm farther away. So bigger the lag time, the farther away you are. But with some more information, like this handy chart right here, we can plot the average speeds for P and S waves through the area that I live in, knowing something about the geology. And so what that can tell me is how far away I am more accurately. Instead of saying, oh yeah, you're farther than me, okay, well that's great. But with this chart, I can say, well, here's my lag time, and then I just come across here and I find out that I'm, 275 kilometers away. And another station would have it's farther away, would have a different lag time. They would look up on the chart and it would tell them, I don't know, they're 475. And the last one would tell me, I don't know, 780. And so using these three, you can just basically draw circles, right? You know where your station is. It tells me how far away I am. I just need a circle with a radius of whatever the distance I am from the earthquake. And if I draw a circle, I know that the earthquake had to have occurred somewhere on that circle. And the reason I have to draw a circle is because I have distance but not direction. So I don't know where it came from. But as long as I have at least two others, for a total of 3 seismograms, I can triangulate and get a location. Now, of course, today with computers, and there's hundreds, if not thousands, of seismographs that are stationed when an earthquake occurs, and that data is collected so quickly, it can be calculated and boom, we say, hey, there's the epicenter, it's right there, and it's confirmed and confirmed and confirmed and confirmed, so we're pretty confident that that's where the epicenter is. Okay, so we need at least 3, right? 3 is all we need, but we probably have, 500, so we definitely know for sure. Okay, so the second thing we want to know about an earthquake is the magnitude. So it gets a little weird, but we'll try to keep it simple. This is an intro class. We don't want to get too crazy on you. But I'm sure you've heard of the Richter scale, and that was the original scale that was developed in California by a guy named Richter. And he used California earthquakes, local earthquakes, and came up with a way to figure out the intensity, energy that was produced during an earthquake. And so his method was actually to measure the height of the S wave. So not the P wave or the surface wave, but the height of the S wave. With enough data, he was able to compare one to another, and he came up with a formula that was logarithmic that basically said if this occurs and this occurs, and I can measure those and I'll give them a number. We use this logarithmic scale where you have 1s, 2s, 3s, 4s. And so you've heard numbers, I'm sure. The Richter scale, there's an earthquake. It was a 3.2, a 5.7, an 8.5. These are measuring the amount of energy released. And so although we could come up with a, calculation, which we don't want you to do, we can still get some estimate. And it seems the best estimate, although we can look at the size of the S wave because it's logarithmic, the deflection of the S wave from one whole number to another is 10 times bigger for one number to another. But that's not, that's a pretty big S wave deflection. I'm not sure that that's a good idea of how much energy was released during the earthquake. So what we're going to do is talk about energy release and relate that to the logarithmic scale. And so there's roughly, it's 30 times. I think it's officially 32 or something. But it's easier to do 30 because it's a nice round number. The energy released between any whole number on the Richter scale or any scale that we're measuring magnitude that's reported in the news is 30 times. So if there's a 5 and then a 6, the difference is 30 times the energy released. That's a lot. And so, of course, between any whole number, so 5 and 6, 30, 6 and 7, 30. Of course, how about between a 5 and a 7? Well, 900 times the energy released between a 5 and a 7. So this is why a 5.2 and a 5.8, they seem pretty similar. But, that's a 0.6. That's at least, 17 times more energy. That's a lot. And so these little decimal points on the Richter scale really do matter. But when we're talking about the difference between, I want you to kind of remember more the energy kind of difference than this deflection of the S wave. Now that I've said all that, officially, the Richter scale was really good for California, but it had some issues with bigger earthquakes, and when we got seismograms around the whole world, wasn't as accurate. So we really use what's called the seismic moment magnitude scale. Now look, it is really similar to the Richter scale, and that the numbers are similar, and it's kind of related back to it. So it's not like a whole new scale. It's still going to have this 30 times energy release difference between one whole number and the other. And it's still reported as, there was a 5.2 earthquake, a magnitude earthquake. Sometimes the news says Richter, but technically that's not true. It is a seismic moment magnitude scale. But I don't want to get into semantics about that or have you be confused about that. The real key, I think, is that I still want you to understand that the difference between one whole number on either of these scales is pretty big, and that's why we care about these numbers. The other one is what's called a modified Mercalli scale. It's still used today, but it's not a scientific scale as much because we're measuring the damage instead of energy. And we do that by basically evaluating the damage that occurred during the event by either going there or talking to people that have experienced the earthquake and say, hey, what did you see and how did you feel and what happened at your house and what happened over here. We take that data and we calculate the ground shaking or the damage that occurred, and we kind of plot that on a map. Both of these give us some information. So the seismic magnitude can be read from a seismogram, but now we're looking at the slip, the amount of area that moved and all that kind of stuff, and the rocks and the strength of things, so we can get a better idea of energy release. If you want to read a little more about it, you can click the link. The USGS has a little story about why we use this scale and not the Richter scale anymore. And then finally, before I'm going to end this video, and I'm going to start another one for the hazards and prediction and stuff, because we're getting a little long, but this is just a list of the Mercalli scale. And you can see off to the left there, they use Roman numerals for this, so they don't confuse it with the Richter or the moment magnitude scale. And this is kind of how it works, and it still works like this today. You can report to the USGS and describe what you experience, and then they will match it up to these kind of descriptions here. If your description matches pretty well with this, and this is even the shortened version. The full version of the Mercalli scale actually has a paragraph for each intensity scale, so a 1, 2. But they would read here and say, oh, that person said that the doors swung a little bit, a couple dishes broken, and it wasn't too bad. So I'm going to give that event a Roman numeral 5 for that person's evaluation of that. And the more data I can collect, I can say, wow, there's a lot of damage locally right here and less damage here. Now, typically, closer to the epicenter, we expect more damage, and that's generally true. The farther away we get, less damage. That's generally true. But not always, because there are factors that influence the amount of damage. You could be farther from the epicenter, but your building that you're in is horrible. It is not constructed well, and it can't survive the ground shaking, and is demolished, where someone closer has an awesome building that was built to withstand it and that doesn't fall down or doesn't sustain as much damage. And you would report that. So you might see that in the data, that there's certain locations that sustain more damage. We would want to know why. Is it structural? That's possible. Is it has to do with geology? It's possible, because different materials behave differently. Loose sediment tends to shake more, and of course, if your building is attached to that, more damage. Hard bedrock, granites and things like that, they're pretty stable. They don't shake as much. And so we could look at the geology to figure that out. And of course, it is subjective. I'm asking people to describe an event. And so people could be off a little bit. If it was horrifying for me, I might describe it as the worst thing ever. Because I've never been in an earthquake, and it was just crazy. Where someone who might have experienced a few earthquakes in their past might downplay it a little bit. So there is some of that going on there too. But it is still data, and it can still be useful for us. And of course, it goes up to 12 on this Mercalli scale. And then the final thing I'll talk about is show you this quick slide. This is just an indication, which I'm sure you're aware, but it's the idea that these small magnitudes, which we're seeing over here on the left, right, occur very frequently, but they're very small. And the big earthquakes are very rare. So, you might get 27s in a year, and a 9 might happen once every 10 years or something like that. So It's just an indication of, how often we get earthquakes. There are lots of tiny earthquakes that you can't feel, but now our equipment is sensitive enough to pick those up. Okay, and if you really care about how many kilometers of explosives, because you happen to be an explosives expert, maybe this is useful to you, but I'm not sure if it is. Okay, so I'm going to end this here, and then in the next one we'll talk about the hazards and some predictions.